Modern artificial intelligence relies on continuous semantic vector spaces to process human language. To understand how these spaces work, we have to look at the mathematical failure of early systems, which treated words as discrete, isolated symbols. The classic approach, one-hot encoding, assigns every word in a vocabulary to its own independent mathematical axis. And in a system with 100,000 words, this creates a vast space with 100,000 dimensions. This grid plots the one-hot vectors for car and automobile. When we calculate their dot product, the result is exactly 0. Because the dot product is 0, these vectors sit at perfect 90-degree angles to each other. Geometrically, the distance between any two distinct words is always a constant, making a car mathematically as distant from an automobile as it is from a cloud. When the distance between points is constant, the derivative of that distance is 0. This means optimization algorithms like gradient descent have no slope to follow. They cannot learn to move related words closer together. The solution is the distributional hypothesis. Instead of encoding a word as a static symbol, we encode the conditional probability of the words that typically appear around it. By focusing on context, language can be translated into a differentiable space, a map where similarity produces a slope that algorithms can actually climb. The first attempt to digitize this hypothesis was building a word context co-occurrence matrix. This process uses a sliding window to scan the text. Every time two words appear within the window, the system increments their shared cell in a massive grid. Because most words never appear near one another, the grid becomes a sparse matrix. Allocating memory for millions of zeros is a massive drain on compute efficiency, especially during the heavy matrix multiplications required by neural networks. To clean up the data, engineers used PPMI. This identifies which co-occurrences are statistically significant and which are just random noise, or common stop words like and or the. They then applied singular value decomposition. By decomposing the matrix into its most significant underlying components, they could discard the 99. Even though the topic is identical, standard Euclidean distance sees these endpoints as being very far apart. Cosine similarity fixes this by focusing on the angle between the vectors. The formula uses a denominator, the product of the vector's magnitudes, to perform length normalization. By dividing each vector by its own length, we force them onto a unit circle. They now have a length of exactly 1, but their original directions remain unchanged. Now the dot product acts as a geometric projection. We are measuring the remaining angle theta between the two lines. By forcing all vectors onto this unit sphere, the measurement is isolated to the algebraic angle of similarity, making it completely independent of word frequency. This proves that in a semantic space, meaning is defined by the direction the vector points, not how long the vector is. In 2013, Word2vec shifted the paradigm from counting words to predicting them using a shallow neural network. This architecture, known as skipgram, maintains two distinct weight matrices, one for target words and one for context words. Using two separate vectors for every word ensures linear stability. It prevents the system from trying to update a word's vector against itself during a single calculation. The computational bottleneck is in the denominator. To calculate a single probability, the system must sum the exponentiated scores of every single word in the vocabulary, often exceeding 100,000 terms. Traversing the entire dictionary for every single training update is an impossible task for real-world datasets. This is the softmax bottleneck. To make predictive embeddings feasible, engineers had to move away from calculating exact global probabilities. They needed a localized solution that didn't require checking every word in the dictionary. The solution was negative sampling. Instead of a massive probability task, the model performs binary classification. Is this word pair real or just random noise? We can see this in the loss function. The blue side handles positive examples. It acts as an attractive force, pulling the target vector and the real context vector together until they point in the same direction. The red side calculates the negative samples. It acts as a repulsive force, pushing the target vector away from random noise words to ensure their vectors remain unrelated. However, picking noise words at random is inefficient. The model wastes time pushing words away from extremely common terms like of or the, which provides no semantic information. To fix this, the system selects noise words based on their frequency raised to the power of 0.75. This exponent flattens the distribution. It decreases the likelihood of picking the most common words and increases the chance of picking rare, information-dense words to act as the negative samples. This contrast of loss function uses geometric force to mold the space, ensuring words used in similar ways are eventually pulled toward the exact same coordinates. When these forces act on a space over billions of iterations, they produce emergent properties, most famously the ability to solve analogies through simple addition and subtraction. Look at the vectors for king, man, woman, and queen. Subtracting man from king isolates royalty. Adding woman points directly to queen, forming a perfect parallelogram. Word2vec factorizes log probabilities, converting ratios into linear differences. Therefore, matching semantic relationships manifest as parallel lines of equal length. This reveals that meaning in these spaces is not just loosely grouped, it is rigidly structured by the rules of linear algebra. Because Word2vec mirrors its training data, it also captures the biases of the people who wrote it, a phenomenon called bias amplification. If the training data contains gender stereotypes, the model embeds them into the geometry. This can cause AI systems to unfairly associate certain technical careers with specific genders. To correct this, engineers use hard debiasing. Using principal component analysis on gendered word pairs, they isolate a single gender axis. We calculate its overlap with the axis, subtract it, and snap the word to perfect neutrality. This is neutralization. We are using orthogonal projection to forcefully strip an unwanted axis of meaning out of a word's representation. Embeddings are not black boxes, they are precise geometric structures. By understanding their linear algebra, we have the tools to audit and correct how artificial intelligence perceives our world.